So, okay, we do an experiment. Mendel did an experiment. Anyone does an experiment, they get a set of data. And if they get a set of data, it looks something like this, with the number of round yellow seed, round green seed, wrinkled yellow seed, and wrinkled green seeds, and then the total number of seeds. We have to consider, are these results significant, or could they have been done by luck? Because remember what we talked about in the past. If you have a coin where you have one side's heads and the other side is tails, well, how do you know that your data, if you're getting 50 heads in a row, how do you know that there's not something wrong with the coin? How do you know it's not a double-headed coin, for instance? Is statistically significant that you're getting 50 heads in a row, right? Because you could get 50 heads in a row theoretically, just randomly, right? It's possible, unlikely, but possible. So the question is there something going on? Anytime we do an experiment, anytime we collect data, there's always that question, is something going on? Or are these results just the result of pure luck? So in science, we're constantly questioning that. Are the results of the experiment something that has happened because of some relationship, some theorized relationship, or is it just due to random luck? Is there a correlation between the events, or is there some random luck? How close are the predicted values, and that's going to be key, predicted values, to how close are our results to the predicted values? Because remember our scientific method, right? We have a hypothesis that it's our scientific guess. It's based on our research and our understanding of what's going on. We have some observations, and we come up with this hypothesis, and we've written it in an if-then statement. If so-and-so is true, then this is going to happen. And so we're predicting some kind of value. And if you remember what the MIT professor said, that when Mendel predicted these values, they were something that were unlikely to have happened coincidentally, right? It was likely that something was going on. So when they looked at that prediction of his hypothesis, and that the predicted values were actually very close to the hypothesis, that was wonderful news for Mendel. But it wasn't perfect, right? It didn't come out to a perfect 3-to-1. It came out to 3.6-to-1. And the question was always, well, was that close enough? Were the results close enough? Or is it something that has to do with randomness? So the chi-square test is a statistical test that helps us analyze the significance of our value. So our predicted value in the case of chi-square is going to say our expected value. So there's going to be some kind of expected value. And when we do these calculations when it comes to genetics, of course that comes with those ratios that we discussed, right? 9-3 to 3-to-1 being one of those big ratios for the dihybrid cross. And there's some other predicted values that we could use. For instance, if you took just one, this is for a dihybrid cross, so this would be like, for instance, if you crossed two heterozygotes for two different genes, right? And there was no, and assuming that there was no linkage, then we would expect to see a 3-to-1 ratio, right? And if we had independent assortment, there's no linkage, then we would expect a 9 to 3 to 3 to 1 ratio. Now we could do it with a simpler cross. For instance, if we had just one gene, if we just looked at one gene, one parent with a single gene, big A or little a, two alleles, and we looked at the results, we might ask, how many, if big A is yellow and little a, the recessive trait is white, then we could predict, right, our expected values that we would have 50% yellow. Oh no, that's not true. Look at that. Look at that. Not paying attention. I hope you caught my mistake before I did. That would make me feel very good. But there would be three out of 4 that would be yellow, and only 1 out of 4 that would be white, because white is the recessive trait, and so only those that had 2 small a versions of the genes would give you a white trait, the white flower. All the other flowers would be yellow, whether they were big A, or they had the heterozygote, or the homozygous dominant, or heterozygote. Irrelevant, they would have the dominant form of the trait. So we could say that there would be our expected values of any kind of heterozygote trait would be 3 to 1, right? 3 yellow to 1 white. And you could do this for every single type of cross, right? So if you could do it for this cross where we'd expect 0% white and 100% yellow, right? In our test cross, this is what we call a test cross, where we have a homozygous recessive cross with a homozygous dominant. And when we look at, if we looked at something like this, we could say we'd expect 50-50, so we'd expect 50% white and 50% yellow, and you can do all kinds of all the different possible crosses and figure out all the different ratios, right? So we'd expect on here to be 50-50 and 50% white. Or another way of saying is 1 to 1. And over here, we'd expect to see 100% yellow, or 1 to 0, right? You'd have no white, 1 yellow to 0 white. So when we're looking at these crosses, our predictive values are what our Punnett squares predict. These Punnett squares are predicting values. They're predicting percentages. They're predicting what we think is going to happen according to Mendel's law of independent assortment, and this concept of are these genes working in a dominant, do these genes produce a dominant and recessive trait, or is there some other type of inheritance going on? So really what we could do is we could predict. We can have some predictions, and then those predictions could be used. Those predictions then could be used to look at actual data and compare the actual data to the predicted values and see if they've come close enough to that data to say, okay, something else is going on. Or is it just due to random luck? So we can't prove anything, and I've said that numerous times in class, but science Science does not prove science doesn't prove what we can't prove, because there's no way to tell whether the next experiment or the next event is going to continue to follow our hypothesis or our theory of how things work. We have these things called phenomenon that we observe. We see things happen. When these phenomenon happen over and over and over and over and over and over again in a very predictable and kind of exceptionally predictable way, we call those laws. But both laws and phenomena are just phenomenons that have very few, if any, exceptions. We have not seen any exceptions to these laws, and so we call these laws, observed phenomenon laws. Theories explain laws. And there's no way to prove a theory. There's no way to say, well, this is really what's going on. There's always that question in the background. What if something else is going on and it just looks like it? What if this theory predicts it and it happens to be right this time, or these first few hundred times, but then something else is actually going on that we don't see? You know, the best example in modern times that I can think of is dark matter, right? So we have this theory of matter, of the universe, where matter has mass and takes up volume, and it reflects light or doesn't reflect light. And yet there's this other stuff now that we call dark matter and dark energy that we think exists in the universe that isn't what we expected. The theory of matter being made of an atom and protons and neutrons and electrons, and there maybe those protons and neutrons are made of subatomic, even smaller particles, but that they create mass and that they share electrons and create bonds, etc. That's all works, so the theory works. However, there's a question: what about dark matter and dark energy? So theories are always, no matter how foundational the idea is in science, there's never a way to prove it 100%. There's no way to say with certainty, with 100% certainty, that this is what we're looking at. So when we talk about science, we are always working in this kind of this uncertainty, with this level of uncertainty for everything that we say. Now, that being said, our theories do explain a lot and allow us to predict enough to be able to build cars and the internet and plastics, and be able to do brain surgery and observe cells functioning. So our theories do work. But we accept the fact that the theories may be not what we expect, that maybe we're wrong in some way that we can't even see. So when we look at theories and when we talk about stuff in science, we don't look to prove things, we look to disprove them. We're constantly trying to disprove a theory. And once the theory's been disproved, then we can move on and restructure it. If it's been disproven enough, if there are enough exceptions to the theory, then we can devise a new theory and throw the old one out. So that goes back to this idea of how many times you have to throw a ball up in the air and it come down for you to prove that every time the ball gets thrown up, it comes down. Well, you have to do it an infinite number of times. So that's not possible. We can't do it an infinite number of times. And that's why we say we cannot prove. Science doesn't prove anything. So what can we do with this ball? And we've discussed this example in the past, so hopefully you remember it. But what could we do, since we can't prove it? We can't prove that every time the ball goes up, the ball comes down. And we can't do it an infinite number of times. What we could do is disprove it. So what we could do is say, how many times does the ball have to go up and then keep going up for us to say that this theory is not correct? That only has to happen once. So it's much easier to disprove something than it is to prove it. And so in science, we focus on disproving things. That being said, what we like to do is we like to think about the hypothesis as not the hypothesis as it stands, but something that we call the null hypothesis. So when we look at the null hypothesis, is the hypothesis that the observed data does not differ from the expected values by any significant amount. So whatever difference we see is not significant. Whatever you observe, the observed relationship, the observed data, the observed is due to random events, right? To luck, whether good or bad luck. Any observed data that does not match what is predicted within some degree of error is considered to be random luck. Otherwise, there has to be another explanation. So either the difference between the predicted and the actual is a big difference or it's a small difference. And if it's a small difference, then it's random and we accept the null hypothesis. If it's a big difference, then we have to consider that there might be something else going on. If Mendel's first law of independent assortment is true, then what we should have is a 9-to-3 to 3-to-1 ratio. That would be when we cross two heterozygote, when we do a dihybrid heterozygote cross, right? So when we cross, round yellow, heterozygous round yellow seeds, when we cross them with each other, what we'd expect is to have a 9-to-3 to 3-to-1 ratio of phenotypes, right? Because that's the phenotypic ratio that we'd expect to see in this cross. So if that's true, that's great, but what we would say is whatever we see, these are the observed results. What we would say is that they're not due. We wouldn't expect 9-to-3 to 3-to-1 ratio, right? So the null hypothesis would say that this is due to random luck, that whatever we got is due to random luck versus, since it's not exactly 9-to-3 to 3-to-1, it's almost never going to be exactly 9-to-3 to 3-to-1. It's going to be something close. The null hypothesis would say that this is due to the results. These results are due to just random luck, whatever it is. So the null says that the relationship is not true. The null says that the results are due to randomness. Null equals randomness. Whatever your theory is, the null hypothesis says it's not true that whatever the results are, it's due to some kind of randomness. Now let's look at the formula for chi-squared. First of all, there's this symbol x squared. This is not x squared. This is the Greek letter chi, and it is a square. It's just a symbol that means chi-squared. It's not actually squared. This is not a variable squared, for instance. This is a symbol that actually means chi-square. Chi-square is the sum. This symbol here means the sum of, and sum just means added, right? All the values added together. Whatever comes after this symbol is going to be added together. So we're dealing with addition. I think everybody's comfortable with addition. I don't think there's any kind of really complicated math here. This means that whatever this is, this whole thing in brackets, squared, another bracket, divided by another bracket. So this whole value, the sum of these things, right, whatever they are, add them all together and you get chi-squared. So what would you, it's the observed value, so that's the value that you see, this would be here, this is the observed value, minus the expected value, those two subtracted, and it's in brackets, so then we would square it, divided by the expected value. So the observed value minus the expected value divided by the expected value. Do that for all the different categories, add them together, that's what the sum means, add all those together, and you get chi-squared. So to look at this example, if we have how many round yellow seeds, round and yellow seeds would you expect to get? You'd expect to get 9 because round and yellow are the dominant. So you're doing this cross, 9 to 3 to 3 to 1. You'd expect to see 9, and you can go back and look at the dihybrid cross in the previous lessons that are in your chat if you'd like. You can go look up dihybrid crosses in your book in the chapter you're supposed to have read. Irrelevant, but the bottom line is that there's 9. You expect to see 9 dominant, double dominant traits, right? Round and yellow seeds. You expect to see 3 that are going to be round, so dominant for shape, but recessive for color, and 3 that are going to be recessive for shape, wrinkled, and dominant for color, right? So 9 to 3 to 3. And then you'd expect to see 1 recessive, wrinkled, and recessive for shape and recessive for color, wrinkled and green. So you'd expect a 9 to 3 to 3 to 1. Now, if you had a total of 556 seeds, and you expect to see the percentage, 9 out of 16. Now, if you go ahead and do the math, 9 out of 16 is about 56.25%. It's horrible. Let me zoom in here. Be about 56.25%. That's what 9 out of 16 is. So if you multiply now if we did a decimal of 56.25, if we did that and made it a decimal, it would be 0.5625. That's what 9 divided by 16 is. And if you multiply that times 556, you get 312. So you'd expect out of 556, 9 out of 16 is 56.25 or 0.5625. You'd expect 9 out of 16. You don't have 16, you have 556. So that 56% of 56.25% of 556 is 312. So this is what we would expect if we had 556 seeds. We'd expect to see 312.75 of them being round and yellow. So the math is kind of simple. You can use it in the calculator. Just plug in 9 divided by 16 in parentheses. Always use parentheses. Multiply that times 556, again in parentheses. I like to use parentheses. They make things simple. And you get 312. Do the same thing for round, green, round, wrinkled. This 3 out of 16 is 18.75. And so each of these is going to be 18.75 or 0.1875. 0.1875. 0.1875. So again, that's 18.75%. Do it any way you want. You can put 3 divided by 16 in parentheses times 556, so you can multiply by 0.1875. no matter how you do it on the calculator, it turns out that what you'd expect to see is 104.25 for both of these, because they're both 3 out of 16. And then if you did 1 out of 16, you'd expect 0.0625. Or 6.25%, right? .25%. So that should be something around 34.75 that are going to be wrinkled to green, or double recessive traits. Double recessive traits. So you'd expect to see 0.0625, 1 out of 16 double recessive traits. There's 556 though, not 16, so multiply times the percentage, and you get 34.75 wrinkled green. These are the expected values. This is what we'd expect. So out of total 556, I'd expect to see 34.75 wrinkled green, 104 wrinkled yellow, 104 about round green, 312 round yellow. But look, we didn't get those results. We got 315, 108, that's not 104. 101, that's not 104. 32, that's not 34. I'm leaving the decimals out, but that's not what we see. So are these results what we expected? No, they're not. They're not. So do we say that there's no relationship? So then do we say that there's no relationship? Do we accept that this difference is due to random luck? Or is there something else going on? The difference from the expected, right? Is it due to random luck? Or is something else going on? Is the difference between these significant? If it isn't statistically significant, then we go ahead and accept that the relationship that we're predicting, the expected values, that the difference between the expected value and the observed value is not due to random luck. If it's not statistically significant, if the difference is not statistically significant, then we accept that the relationship is still valid, it's still working, it's predicting within some kind of accuracy that's acceptable. So that takes us to this table here. Well, first let's figure out what we have to do. How do we get chi squared? This is chi squared. Remember, it's not x squared in this case. This is chi squared. This is the Greek letter chi, and that's the 2 just means squared, so chi squared. All right, so we take 315. So we take 315, which is the value that we've observed, minus 312, which is the 0.75, which is the predicted value. We square it. We divide it by the predicted value or expected value, 312.75, right? That's what the formula says to do. We subtract these two, square it, and divide it by this. That's 1, but then we have 1, 2, 3, 4, 5, and 4. We have 4, right? So 1, 2, 3, 4. We do it 4 times and add it together. Why? Because you're taking the sum of these. It's not that hard. So we have 4 possible classes, 4 categories. We have to calculate something called degrees of freedom. Degrees of freedom is a statistical number that looks at the possible states that something could be in. And the way it's calculated is just you take all the different categories that are possible and subtract 1. And that's the amount, those are the abilities, the different states that they can switch into. So it's 4 minus 1. To be honest, the exact definition has always eluded me, but that's what the statisticians define it as. So if you want to, you can go and look at, I will post a reference, and you can go look at the actual statistical definition. But the easiest way to think about it is you take the number of categories, so in this case there's 4, They could be either yellow seed round, green seed round, yellow seed wrinkled, or green wrinkled. So 4 possible states. Subtract 1, and those are the degrees of freedom. So they have the ability to switch into 3 other states, right? This is where they're at, and they can switch between. There are 3 other possibilities other than themselves. So it's how many total categories you have minus 1. So in this case, it's 4 minus 1. So our degrees of freedom are 3. This is going to be a very important number. And by the way, it'll be important in all kinds of statistics. So make sure you understand that whatever your categories are, you subtract 1, and that's going to be your degrees of freedom. Your chi-square, once you've done all this math, is 0.47. So if you go ahead and if you do all this math, you're going to end up with a number of 0.47. So reasonably, you see that these numbers all added together equal 0.47. Now that might seem kind of odd because these numbers are so big, but consider 315 minus 312 is a small number, even after it's squared and divided by a big number is going to be some kind of decimal. So you add them all together and you're going to get this decimal. Okay, so you enter chi-square at the table with a degrees of freedom of 3. So let's take a look at this. Here's this table. It's called the chi-square table, and the number that the probability that we want to look at is this one. Is 0.05. 0.05. This is the one we want to use. Now, what this means is that this probability, there's a 95% chance that whether you accept it or not, they accept the null hypothesis, or you accept that, and if you accept the null hypothesis, you're saying that if you accept the null hypothesis, you're accepting that nothing else is going on outside of what you predicted. If you accept the null hypothesis, you're saying that there is no statistically significant, if there's no statistically significant difference between your value, your expected value, or that from that's been observed. So there's, in this column, if your value is, so when we're looking at 0.05, what we're saying in the probability of 0.05, you're saying that if the value, the critical value, which is these numbers, all these numbers are called critical values. These critical values, these decision-making points, right? That's why we call them critical values. If they're if the value, if your chi-square, in this case 0.47, is greater than this critical value, in this case, if it's greater, if our chi-square is greater than our critical value, then we're going to reject the idea that the difference here, the difference between the two, is not significant. So that we would reject that at 93 to 3 to 1 predicted value, that this fits into the 93 to 3 to 1 predicted value. If it's less than whatever the critical value is, 0.47 is less than whatever the critical value is, then we would accept that the data fits the 93 to 3 to 1 ratio that's predicted. So the question is, does it fit? Do the observed results fit well enough with the predicted results? If not, we just accept that it's due to random luck. So if it's due to random luck, then we're not going to accept the idea, the hypothesis, but rather the alternate hypothesis. So now let's take a look at what we're talking about here. We're talking about a theory a theory that says that, well, these genes are not linked, right? These two genes, this gene that gives you round shape or wrinkled, right? The two alleles that give you round or wrinkled, and the gene that gives you green or yellow, the two alleles that give you green or yellow, that they're not linked. So they're randomly assorting. And so therefore, that again, what does that mean? That the genes are not on the same chromosome, right? Or at least that they're not close together on the same chromosome. So that the distribution of frequencies of the likelihood of inheriting these genes are going to be 9 to 3 to 3 to 1. So when these two heterozygotes, double heterozygotes, right, when they have babies, their babies are going to be 9/16, 9 out of 16 are going to be round and yellow, 3 out of 16 round and green, 3 out of 16 wrinkled and yellow, and 1 out of 16 green and wrinkled. So that the hypothesis is that they are not, these two genes for color, seed color, and seed shape are not linked. So if this distribution here, these actual numbers match close enough to 9 to 3 to 3 to 1, then the genes are not linked. So in the null hypothesis, any difference between the observed, the predicted, and the observed, the predicted or expected and the observed, any difference is due to random luck. So the null says any difference between the predicted values and the observed values is due to random distribution of outcome or luck. So any difference between the expected, these numbers here, and the observed values here is due to random luck. The alternate hypothesis, which is to say the hypothesis that is opposite the idea that it's due to random luck, is that it's not due to random luck, but rather that something else is going on. In this case, is that the genes are not independently assorting. In other words, that I put asserting, but it should be assorting, but rather that they're linked. They're close together on the same chromosome. So again, how are we going to be able to tell the difference between which one is true? Are these genes, do we accept the null hypothesis, or do we reject the null hypothesis and then accept the alternate hypothesis, right? So we either accept the null hypothesis, there's no significant difference between the expected values and the observed, or we reject the null hypothesis and we accept the alternate hypothesis. That again, in this case, is that it's not due to random luck, but that something else is going on, and in this case, that something else is that the genes are linked. So how do we tell? How do we look at this data and tell? Well, we're going to use chi-square. So there's the accuracy of your data can be determined to about a 95% accurate confidence, to 95% confidence. If we look at 0.05, so look at the column at 0.05. If we look at 0.01, that's even more accurate. This is 95, you're 95% confidence here. This is even going to be more accurate. This result's going to be more accurate. We can go up to, in this case, it would be 99% confidence that somewhere, that the real answer is somewhere within in your data if the chi-square is smaller than these values, than these critical values. We tend to, for most of the work that you're going to do in biology and And in medicine or in business even, most of the time you're looking at 95% confidence in your result is pretty good. So if you can find, most of the time you're going to use 0.05. Sometimes you don't need as much you have so much data, or you don't really need that great a level of confidence. So you can actually take it down, say 90. You can go as low as 10% here, right? 90%, 50% confidence, 10% confidence. For whatever reason that we're not going to get into in this class, you can actually decrease the probability that you're right. Here at this probability of 0.05, 95% confident that you're going to be here, that if your critical value is greater than your chi-square, in other words, your chi-square is smaller than your critical value, right? Then at your degree of freedom, which in this case was calculated at 3, so your degrees of freedom at 3. So at 0.05, if your chi-square is less than or equal to 7.82, then you're going to accept the null hypothesis. So let's go ahead and again, we looked at the data, and I'll put it out step by step for you because you're going to do a problem set soon. You're going to look at the expected values, figure out what those expected values are. In this case, we know our expected values are here. Why are these the expected values? Because we expected 9 out of 16. 9 out of 16 would have round and yellow, and we had to find out the total. The total was 556 seeds. That's how many we actually calculated. So we would have expected 312 of them to be round and yellow. What we got were the observed values, the values that someone counted, and that was 315. So then we go ahead and subtract the observed minus the expected. Again, remember the parentheses. You square that. You divide it by 312, which was 0.75, which was the expected value again. Write that down. Then you add the round green seed probability minus the observed, or the observed minus the expected divided by the expected. Of course, you square it. Don't forget to square it. Now, these squares actually do mean square, so you want to use that in the calculator. This square does not mean square. This is just chi-squared. It represents the name of the formula. And you add those up. That's part of this. That's what this symbol here means. It means sum. It means sum to add together. So you add those numbers together, and you get a number. In this case, that chi-square value is 0.47. Then you figure out what your degrees of freedom are. Here you have to use this table, which I will include in any problem set that you have. There's your degrees of freedom. The degrees of freedom are, you look at how many different categories you have. In this case, there's 4. You subtract 1, that's 3. So there's your 3. You find the 0.05. Always look at that 0.05. Because that's your 95% confident you're going to have the right answers somewhere in this data set. So 7.82. Anything less than 7.82, you can go ahead and accept it. Any difference less than 7.82, and of course 0.47 is a lot less than 7.82. So you can confidently say you can accept the null hypothesis that this data, the difference between the expected value and the observed value is not significant. Is not significant. If it were significant, if the difference were significant, if these numbers were, and you can't really tell just by looking at them, you have to do this math. If the data is not, if it was significant, if these numbers were off by a lot more, and they were significant, we'd have to reject the null hypothesis and then accept the alternate hypothesis, which in this case is that these genes are linked and that they're not independently assorting. All right, so let's write down the steps before I let you go to do your problem set. So the first step is you have to figure out what are the expected values. Now, how are you going to do that? You're going to use what you know, usually the Punnett square or known ratios like 9 to 3 to 3 to 1, but somehow the theory predicts something. Your theory or your hypothesis predicts an outcome, right? That's what theories do. That's why they're in science. Hypotheses and theories are so important because they allow you to predict something. In this case, 9 to 3 to 3 to 1 is the predicted value. So you use the theory, and you predict the value. Then the second thing, you have to look and you have to find what are your observed outcomes. Either you do the experiment or you have to have that data given to you. The third question is what you're going to have to find. You're going to have to take, usually, let me just put it this way, usually your predicted values are percentages, right? So you're going to look at 9 out of 16, for instance. Again, 9 out of 16 is 56.25%, right? Or 0.5625. So you're going to use your predicted values. You're going to figure out what those predicted values are, and those predicted values or expected values are going to be, you're going to use the theory, and usually you're going to use those percentages. But that means that you're going to have to, you will, in genetic problems, in problems where you're using chi-square on genetic problem sets, you're going to have to calculate the total population you're working with. And in this case, it was 556, if you remember correctly. We added up all the total, all the progeny, and we came up with 556, whatever that total is. And then use the percentages, the percentages predicted to come up with predicted values that will allow you to use in the chi-square formula. So again, in genetic problems, you're going to have, to get your expected values, you're likely going to have to take some kind of percentages. In this case, it's 9 out of 16, 3 to 16, 3 to 16, and 1 out of 16. But sometimes it'll be 3 to 1, or it might be 50-50, whatever the percentages are. And then you're going to have to multiply times the total of the outcomes. In this case, again, we're 556, but it could be 10,000. It could be 20. It could be a lot of numbers, any number, depending on how many progeny you have. Then use the percentages predicted to come up with the predicted values, right? So the percentages that the theory tells you you should have, and multiply times the actual number of outcomes, and the outcomes here are seeds, but the outcomes could be baby humans or baby kittens or baby dogs or whatever it is. Those are the predicted values. Now that you've multiplied the total by the percentages, and you make sure you write it down into a table like this one is, expected values for each of the categories. Those are your expected values now. Now you have your expected values. Your observed values have to be given, or you have to actually count them, right? You have to do the experiment and count them. So this is what you expected. These are what you expected. These are what you got. So the next step is you're going to use chi-square. Use the chi-square formula. So step 3, use the chi-square formula like we just did, and it will be given to you and every time you have a test in this class. Use the chi-square formula to determine chi-square. Now, please remember to use these parentheses appropriately. Don't make the mistake of subtracting, then dividing, then squaring, or dividing and then subtracting, then squaring, or some combination of a problem with order of operations. So subtract, square it, divide it, write that number down. Plus subtract, square it, divide it, write that number down. Do them for each category, add them up. Then you get your chi-square, and you're sure then that you did it correctly. Whatever is inside the parentheses first, then square it, then divide it. All right, remember your order of operations. So after you found your chi-square, the next step is, what are your degrees of freedom? Now, your degrees of freedom are going to be calculated by the number of categories or possible states minus 1. Right? And what do I mean by possible states? Well, in this case, in this example, the one possible state is round yellow seed, another possible state is round green seed, another possible state is wrinkled yellow seed, and another possible state is wrinkled green seed. So there's 4 possible outcomes or states that these embryos could be in. And those 4 minus 1 is 3. And that's where we get this 3. That's how you read this chart. So now at this point, let's go down the list. We know what our expected values are. We know what our observed values are. And I don't know why I put outsources there. I don't know if it's, I'm just trying to let's just use values. So we're using the same vocabulary. What are your observed values? So you know your observed values. It's best you write it into a table. I mean, really, just write it into a table. You can be lazy, but what it's going to do is it's going to end up completely confusing you. So just make sure you write down your expected values in one column, your observed values in the other column. Make sure that you're doing the right calculations, you're applying the right formulas, right? The right predicted percentages for each one. You have your observed values. Those are either given to you or you've counted them in a lab. Then you use your chi-square formula to determine the chi-square by making sure you're following the order of operations. You're remembering that this is not x, it's chi, it's the letter chi. This symbol in the formula means sum. You're adding these together. All right. What are your degrees of freedom? You calculate that by the total number of categories, in this case 4. Minus 1 would be 3. All right. Then you read the chart. Then you just read the chart. So the 5th step is you use the chart How do you do that? Well, you find your degree of freedom. Again, in this case, it's 3, so you'd go down to 3 here, right? You come across. But in another problem set, it might be less. It might be only 2 categories. And if it's 2 categories, then it's 2 minus 1, which would be 1. So there's only one. There's 2 minus 1 is 1. So you'd use the first row. If it's 6, it's 6 minus 1. So that's use the 5th row, etc. And the rows, there's more rows. In this problem set, they only give you 5 rows because you don't need, all you need is the 3rd row, really. You find your degrees of freedom. go across, and the second part of that using this chart is you go across to 0.05, a probability of 0.05, or 95% confidence that you're gonna that this result will be accurate enough for you to be able to tell whether to accept the null hypothesis, to tell if there's a statistical significance. So at this point, now you have your value. Now you've come across to 0.05. You have found your degrees of freedom. You went to that degree of freedom. Again, in this case, it's 3. You went across to 0.05, and you found your critical value. So at finding your critical value, well, so now find your critical value. That's going to be the value you're going to compare it to, because the last step in this is compare your chi-square value to the critical value. And if your chi-square is less than the critical value, right, then you accept the null hypothesis. If it's greater than the critical value, then you reject your null hypothesis and accept the alternate hypothesis. So you're going to use this, in this case, 0.47, compared to a degree of freedom of 3 to 7.82. 0.47 is less than 7.82, so I'm going to accept the null hypothesis that the difference between the two, the expected and the observed, is due to random noise, and that I will accept the null hypothesis that there is the relationship of 93, the predictive values of 93.3 are what's going on, and there is no other explanation necessary. On the other hand, if that number would have came back at 8 or 8.85 or some number that's larger than 7.82, then I would have to say that I'd have to reject the null hypothesis and accept the alternate hypothesis. And of course, the alternate hypothesis in this case would be that the genes are linked. So when you're doing a genetics problem like this, you have to first understand what is being predicted. What is the hypothesis? What am I predicting? So that's this, right? I'm predicting that it's going to be 93.3. The null hypothesis is that any difference I see between the two is due to random noise, and therefore I expect that the chi-square will be less than the critical value at whatever degree of freedom. But I also have to know what the alternate hypothesis is. So I'm expected to do this statistical stuff, this adding and subtracting, yes, some squaring involved as well. You need to follow the steps and the orders of operation. That's true. But you also have to understand what is being predicted, what is the hypothesis, right? So in order to get the null hypothesis, in order to get these expected values, you're going to have to be able to calculate, you have to be able to predict, so you have to know the hypothesis. And then you have to understand what is the alternate. If there is something else going on, what is that other thing? So I have to understand the context as well as the math behind it. All right, so that's the genetics, and now you have an assignment that's going to be given to you that is that's going to be posted in Schoology. It's a POGIL, a chi-square POGIL. So complete that, and we'll talk at our next session. All right, have a good one.